Oh, class, that's the bell. Let's settle down, everybody. It's time to start. What we're going to do today is we're just going to watch YouTube videos. So it's going to be like one of those YouTube videos in a YouTube videoception, if you will. So like one of those bad reaction videos on YouTube. So today what we're going to watch is how batteries work. So now that we've kind of learned what voltage was, this term called potential difference, meaning electrons have potential energy as they move from, or as they want to move from one place to another, we're going to talk about how batteries work, how they harness this idea of voltage, and how we can get useful work done from that. So let's start out with this video called How Batteries Work by Adam Jacobson. Let's give it the old full screen. Let me put on my sweet headphones. Nice. All right, let's do it.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment.
So just yet another example of how physics is the one true science and can answer the questions of biologists and chemists. Just, classic example. No big deal.
He tested his idea with a stack of alternating layers of zinc and copper separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water.
So this is kind of the basis for how batteries work. You have tons of excess electrons in one section, which would be the blue zinc section, and a lacking number of electrons here in our copper section. So those electrons desperately want to get to the other side. And if we connect them with a wire from one end to the other, those electrons can travel to the other side.
In a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste. But the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly.
This is why you guys complain about your phones when they get older. The more you charge your phone, the more little errors in the surfaces of the metal that are going to occur, and the worse it's going to be with its charge later on. So what's really important with your phone batteries is to make sure that you're charging them as little as possible. So ideally, in an ideal world, you would use your battery almost all the way to 0%, and then you would sit and let it charge to 100% all in one shot, and then take it off the charger as soon as it would hit 100%. So obviously that's not practical, because we're all addicted to our phones, especially probably now. But that is the best way to take care of your batteries, to limit the number of times you're actually recharging it.
The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall, rather than expending one battery to charge another, is your best bet to forestall that fatal bleep.
Well, giving credit to everybody, just so I don't get sued by YouTube. Let's leave that up for a second. So I find this really interesting because the basis for how a battery works, as you can see, is all about really a battery is two objects. It's a positive and a negative end. So if we look at this Energizer battery, we have our positive end and our negative end, as all of you guys should know because you've put a battery into something before, right? So as you put this battery in, you have to pay attention to which end is which. So the negative end, which we'll call it this silver end of this classic AA battery, is filled with tons of excess electrons. It's very negatively charged. And the black part, the positive end, is lacking electrons. So the electrons in the silver end desperately want to get to that positive end. But there's something inside that battery, which is actually a chemical reaction, keeping those electrons from getting over there. So if we connect both sides of the battery to one another, we can connect them and the electrons will flow from one end to the other. So this flow of electrons is useful. We can use the energy that these electrons have to do meaningful work for us, like light up a light bulb or power your phone. So these batteries, these AA batteries, these have about 1.5 volts of potential difference. A 9-volt battery has, you guessed it, 9 volts of potential difference. And then this is a car battery. And you'll notice all three of these batteries, this one, and this one, have positive and negative sides to them. They're all essentially two objects, one side that's very negatively charged and the other side that's positively charged. So those electrons want to go from the negative side of that battery to the positive side. So this next video is just kind of an interesting thought that might occur to you, maybe if you were isolated due to, a worldwide pandemic, you might do something like this. But this guy did this in 2011, so he just has no life, really. Let's watch it.
Guys, here we have a used 9-volt here, and if we take an alligator lead and we short the battery out, you see a little bit of a spark.
So we call that an alligator lead, also known as an alligator clip. And that's this clip right here. We call it an alligator clip because it looks, like an alligator, Okay. I just figured I'd explain it.
I don't know how well it's showing up on the video there, but you can see just the faintest of spark. So I got an idea. So I had more than one of these, right? So I have a 9-volt battery here, and if you take another one here, and you don't do this dumb trick that we all did when we were little.
Yeah.
But you shift this over and you put these in series. Now you have the voltage from this one and this one. So now if you take the same alligator leads, now you probably have a little bit of a bigger spark. Get the camera here. it's just a hair bigger. So then I was thinking, well, what if I have, a couple of these things laying around?
Naturally.
Let's see how big of a spark I can make.
Yeah, of course.
So let's find out. So it turns out that I had about 244 of these guys laying around. And so as you can see here, if this doesn't make you dizzy, what I've done is I just put these guys all in series. I put all the leaves in my table, and I ran out of room, so I made a second column up top here and just connected them with jumper cable. So I did a measurement. Now theoretically, this is a lot of volts. I didn't even do the measurement, but it's 244 batteries. These are used batteries. They're not all new. I didn't buy these. I don't have that kind of money or spare time.
So what he's saying here is ideally this should be 944 or 9 volts times 244. So if we do that math real quick, we end up with, excuse me, I got my calculator here. 9 times 244. This should be 2,196 volts, which is quite a lot. However, he's saying some of those batteries are used. So that actually means that they would have less potential difference. So as a battery is used, the electrons are moving from one side to the other, meaning the silver side of this battery, which we'll say is the negative side, has less electrons. It's less negatively charged. And this positive side is gaining more electrons as they move over. So we'll say it's become less positively charged. So the difference in charge, the potential difference, is smaller.
But I did a voltage reading with my meter in chunks, and it's about 2,000 volts DC. So we're going to hook this up, and we're going to see what kind
calculations.
of arc 2,000 volts DC gives. All right, guys, this is about 2,000 volts. You can see my alligator clip's a little bit charred because I just did this a little bit ago. But here, I just want to show you, this is what happens when you arc these things. That's it's quite a bit there. I don't know if you can see that.
It's quite a bit.
I'm going to back this camera up here.
So what we're seeing here is actually the electrons transitioning from excited states down to their regular states in the air itself. So that's what's giving off the light. Any fire you're seeing is actually just the little bit of rubber on the outside of his alligator clip that he's using that's catching on fire from the sheer amount of heat. So this isn't causing fire in any way, just like lightning doesn't cause fire directly. All it does is causes a tremendous amount of heat. And if something flammable is nearby, like a tree or rubber in this case, it can actually catch fire. Now, was this dangerous for him to be holding that closely? Actually, not really. In this case, all of those electrons are trying to get to the ground, or since they're not being allowed to, they're trying to get to the positive end of all these batteries. Since they really want to go to the positive end of the battery, more so than they'd want to go to this neutral person's body, it's actually not that dangerous for him to hold. This is the same way that, birds standing on electrical wires isn't that dangerous either. The electrons want to go from one side of that wire to the other side more so than they'd want to go through that bird.
It's pretty awesome.
It's pretty
Next,
awesome.
we're going to blow up some components. Children, don't do this at home.
Guys, don't do this at home. We're not going to watch the next part because it's tremendously boring. If you guys want to search up the video and watch the rest of it on your own in the amount of spare time that you guys have, you may go and do that. But your homework tonight now is going to be using this circuit construction kit. We're going to start talking about circuits now and talk about how we can use the movement of electrons to actually do meaningful work. So what you have here is you got a wire, a battery, a light bulb, so on and so forth. What I would like you guys to do is create a circuit. Whatever that means, I want you to create a circuit, and I want you to get the electrons to move from one side of the battery to another. That's it. Just get the electrons to move from one side of the battery to another. That is your only job in tonight's homework. All right? So I will put this link on Classroom. obviously, because you clicked on this video, which was part of that classroom post. So just make sure you go do the homework. All right. So that'll do it for today, ladies and gentlemen. Another day of physics in the books, and there's the bell. It's time to end class.